"40 light-years from Earth, there's a planet that might just be our twin." Scientists call it TRAPPIST-1E, and if you're waiting for the usual disclaimer about how we'll probably never know if it's habitable, you might want to sit down. Because what we've learned about this world in the last few years has fundamentally changed that conversation. This isn't speculation wrapped in maybes. TRAPPIST-1E is 92% the size of Earth, has 82% of our gravity, receives 60% of the sunlight we do, and sits precisely where liquid water could exist on its surface. But here's what makes this discovery different from every other Earth-like planet we've found. We're actually measuring its atmosphere right now. Or at least, we're trying to figure out if it has one, which sounds less exciting until you realize what that really means. The James Webb Space Telescope has already observed this planet 4 times, collecting data that's forcing scientists to completely rethink how we study distant worlds. The readings are confusing, contradictory, and absolutely fascinating. Some signals hint at methane. Others suggest a bare rock with no air at all. And that uncertainty, that's not a failure of science. It's the sound of us standing at the edge of actually knowing something concrete about a world dozens of light years away. Let me put this in perspective. When astronomers discovered the first exoplanet around a sun-like star in 1995, they found a gas giant orbiting closer to its star than Mercury orbits our sun. It was called a hot Jupiter, and it made absolutely no sense based on everything we thought we knew about planetary formation. That discovery won a Nobel Prize because it shattered our assumptions. TRAPPIST-1E isn't shattering assumptions. It's confirming our hopes while simultaneously making everything more complicated. The planet completes one orbit every 6.1 days. That's not a typo. A full year on TRAPPIST-1E lasts less than a week here on Earth. It orbits at a distance of roughly 3% the separation between Earth and the Sun, which sounds absolutely catastrophic for habitability until you learn about the star itself. TRAPPIST-1 isn't like our Sun. It's what astronomers call an ultra-cool dwarf, with a surface temperature of about 2,500 Kelvin compared to the Sun's 5,800. Its mass is only 9% of the Sun's. Its radius is barely larger than Jupiter's. And here's the part that changes everything about this story. TRAPPIST-1 will shine for 10 trillion years. Not billion. Trillion. That's roughly 700 times longer than the current age of the entire universe. Think about what that means for a moment. Our Sun has maybe 5 billion years left before it expands into a red giant and incinerates the inner planets. TRAPPIST-1 is just getting started. It's between 5 and 10 billion years old already, potentially twice the age of our solar system, and it has essentially forever ahead of it. If life emerged on TRAPPIST-1E at the same pace it did on Earth, it could have had billions of additional years to develop before humans even existed. But we're getting ahead of ourselves. First, we need to understand what this world actually looks like, and that's where things get genuinely strange. The star would dominate the sky. From the surface of TRAPPIST-1E, TRAPPIST-1 would appear 4 times larger than the Sun does from Earth, covering an angular diameter of about 2.17 degrees. It would glow a deep orange-red, not the yellow-white of our Sun, because most of its radiation pours out in the infrared spectrum. Stand on this planet and you'd be bathed in perpetual twilight, with visibility extending into wavelengths our eyes can't detect. And you'd never see that star move. TRAPPIST-1E is tidally locked, the same side always facing the star, just like the moon always shows Earth the same face. One hemisphere experiences eternal day, the other, eternal night. The terminator, that boundary between light and dark, would be a ribbon of permanent sunset circling the entire world. This might sound like a death sentence for habitability, and for decades scientists assumed it was. How could life exist on a planet where one side roasts under constant starlight while the other freezes in endless darkness? But climate models have revealed something unexpected. A thick enough atmosphere could redistribute heat from the day side to the night side through powerful atmospheric circulation. Winds would howl across the terminator at speeds that would make Earth's hurricanes look gentle, carrying warmth into the darkness and cooling the scorched hemisphere facing the star. The habitable zone might not be the entire surface. It might be that thin band where day meets night, where temperatures could stabilize somewhere between the extremes. Imagine a world where all life exists in a narrow strip circling the planet, with frozen wastelands on one side and baking deserts on the other. That's not science fiction. That's a legitimate possibility we're actively investigating. Now here's where this story takes a turn that should honestly keep astronomers up at night. TRAPPIST-1E isn't alone. 6 other planets orbit the same star, all of them Earth-sized or close to it, all of them packed so tightly together that the entire system would fit comfortably inside Mercury's orbit around our Sun. The distance between TRAPPIST-1B and TRAPPIST-1C at their closest approach is only twice the distance between Earth and the Moon. From the surface of TRAPPIST-1E, you wouldn't see stars at night. You'd see planets. 6 of them, some appearing larger than our moon, moving in complex patterns across the sky as they orbit their common star. They wouldn't be distant points of light. They'd be visible disks, recognizable worlds, close enough that you could potentially see surface features with a decent telescope. 3 of these 7 planets, TRAPPIST-1E, F, and G, orbit within the habitable zone. Not 1. 3. This system doesn't just give us a single chance to find life. It gives us multiple opportunities within the same stellar neighborhood, all close enough to study with existing technology. The orbital configuration is almost absurdly precise. The planets exist in what's called a resonant chain, where their orbital periods relate to each other by near integer ratios. Take one planet's orbital period, divide it by its neighbors, and you get simple fractions like 3 to 2 or 5 to 3. This isn't random. It's the signature of planets that formed together and migrated inward as a group, their gravitational interactions locking them into a cosmic dance that's remained stable for billions of years. That stability matters more than you might think. These planets pull on each other constantly, their gravity creating tidal forces that could generate internal heating, potentially maintaining geological activity long after the planets should have cooled into dead worlds. Active geology means volcanism, which means gases being pumped into the atmosphere, which means a mechanism to replenish air that stellar winds might strip away. And those stellar winds are vicious. TRAPPIST-1 produces frequent flares, 42 detected in just 80 days of observation. Its magnetic field is roughly 600 times stronger than the Sun's. The stellar wind pressure at TRAPPIST-1E's orbit could be 1,000 times greater than what Earth experiences. Over hundreds of millions to billions of years, that wind could strip away atmospheres from the inner planets, including TRAPPIST-1E. So if TRAPPIST-1E has an atmosphere after all this time, after billions of years of bombardment by stellar radiation and powerful winds, that would tell us something profound. It would mean the planet has found a way to hold on to its air, either through a strong magnetic field of its own, or through geological processes that continuously replenish what's lost, or through sheer atmospheric mass that can weather the assault. Which brings us back to the question we're actually trying to answer right now. Does TRAPPIST-1E have an atmosphere at all? The honest answer, based on 4 James Webb observations, is that we don't know. The data suggests 2 equally possible scenarios. Either the planet has a dense, nitrogen-rich atmosphere similar to Earth's, possibly with traces of methane. Or it's a bare rock with no substantial air whatsoever. Both options fit the current observations. Both are consistent with what we know about planetary evolution around ultra-cool dwarfs. And both would teach us something essential about how planets retain or lose their atmospheres over billions of years of stellar violence. But we need more data, and that's exactly what's coming. 15 additional James Webb observations are planned, using an innovative technique that might finally settle the question. The technique involves observing TRAPPIST-1B alongside TRAPPIST-1E during back-to-back transits. TRAPPIST-1B, the innermost planet, is almost certainly a bare rock. It's too close, too hot, too bombarded by stellar radiation to hold on to an atmosphere. When JWST watches TRAPPIST-1B cross in front of the star, any signal detected is purely stellar noise, contamination from the star's own activity rather than atmospheric absorption. Scientists can then use that noise signature as a baseline, a reference point to subtract from TRAPPIST-1E's observations. It's like having a control experiment built into the same stellar system. This approach sidesteps the fundamental problem that's plagued exoplanet atmosphere detection for years. When you're trying to detect the chemical fingerprints of an atmosphere by watching starlight filter through it during a transit, you're measuring incredibly subtle changes. The planet blocks maybe 1% of the star's light at most. The atmosphere, if it exists, absorbs maybe 1/100th of that. You're looking for a signal that's 1 part in 10,000, and the star itself is variable, flickering and flaring in ways that can easily mimic or mask an atmospheric signature. Using TRAPPIST-1B as a reference planet is brilliant because it eliminates the guesswork. Both planets orbit the same star, experience the same stellar activity, and can be observed in quick succession before conditions change significantly. Any difference between their transit spectra has to come from TRAPPIST-1E itself, not from stellar variability. If TRAPPIST-1E has an atmosphere, this method will reveal it. The 15 additional observations should provide enough data to move beyond educated guesses. 4 transits gave us a tantalizing maybe. 19 total transits, combined with the reference planet technique, should give us an answer. Not a perfect answer, not complete atmospheric characterization, but a definitive yes or no on whether air exists around this world 40 light-years away. While we wait for those observations, there's another mission preparing to contribute. Pandora, a small satellite scheduled to launch in early 2026, is specifically designed to study exoplanet atmospheres and their host stars simultaneously. It won't have James Webb sensitivity, but it'll provide continuous long-term monitoring that space telescopes like JWST, which must divide their time among thousands of targets, simply cannot match. Pandora will watch TRAPPIST-1 for extended periods, building up detailed profiles of the star's behavior and how it affects observations of the planets. This multi-pronged approach represents how modern astronomy tackles the hardest questions. No single observation definitively answers whether TRAPPIST-1E has an atmosphere. Instead, we build the answer through layers of evidence, each observation constraining the possibilities, each new technique eliminating alternatives until only one explanation remains consistent with all the data. But let's assume the best case. Let's say the upcoming observations confirm that TRAPPIST-1E does have an atmosphere. What would that atmosphere actually be like? Climate models offer some intriguing possibilities. The most likely scenario, if an atmosphere exists, involves a dense nitrogen-rich envelope similar to Earth's but potentially thicker. Nitrogen makes up 78% of Earth's atmosphere, and it's chemically stable, not easily stripped away by stellar winds or lost to space. A nitrogen atmosphere on TRAPPIST-1E would suggest the planet formed with substantial volatile compounds, retained them through billions of years of stellar assault, and maintains geological activity that continues replenishing atmospheric gases. The models also hint at methane, which is where things get really interesting. Methane in Earth's atmosphere comes primarily from biological sources. 90% of atmospheric methane on Earth is produced by life, from bacteria in wetlands to microbes in the guts of animals. The remaining 10% comes from geological processes, volcanic activity, and the breakdown of organic material. Detecting methane on TRAPPIST-1E wouldn't be proof of life. There are plenty of non-biological ways to produce methane. Saturn's moon Titan has an atmosphere rich in methane, and there's no life there. Geological processes can generate methane through reactions between water, rock, and heat deep beneath a planet's surface. But methane's presence would raise the question, and it would raise it loudly. The challenge with methane is stability. In Earth's atmosphere, methane breaks down relatively quickly, destroyed by ultraviolet light and chemical reactions within about a decade. The fact that Earth's atmosphere contains methane despite this constant destruction means something is continuously producing it. The same would be true on TRAPPIST-1E. If we detect methane, something must be generating it faster than processes can remove it. Carbon dioxide is another gas the models consider essential for habitability. Even small amounts, just a fraction of 1%, could provide enough greenhouse warming to keep surface temperatures above freezing. TRAPPIST-1E receives about 60% the stellar flux that Earth receives from the Sun. Without greenhouse gases, the planet would be frozen. With the right amount of carbon dioxide, liquid water becomes possible. The equilibrium temperature calculations place TRAPPIST-1E somewhere between 225 and 246 Kelvin, depending on how much light the planet reflects back into space. That's cold, roughly -48 to -27 degrees Celsius. But those numbers assume no atmosphere and no greenhouse effect. Add a modest atmosphere with some carbon dioxide, and the surface temperature could rise above the freezing point of water. Water is the real question mark. Density measurements suggest TRAPPIST-1E might be slightly less dense than Earth, which could mean it contains more water. Some studies estimate the planet could hold water equivalent to several Earth oceans, possibly as much as 5% of its total mass compared to less than 1% for Earth. If that's accurate, TRAPPIST-1E might not just have oceans. It might be an ocean world, a water planet with a global sea potentially hundreds of kilometers deep, nothing like the continents and ocean basins we're familiar with. Ocean worlds present their own habitability challenges. Too much water and you might lack the rock-water interface where chemistry happens, the shallow seas and tidal zones where life on Earth first emerged. Too much water and plate tectonics might not function properly, eliminating the geological recycling that keeps Earth's carbon cycle running. But too much water doesn't mean uninhabitable. It means different, an environment where life, if it exists, would have to work differently than life on Earth. The tidal locking adds another layer of complexity to any climate model. One side of the planet faces the star permanently, receiving constant illumination. The other side faces eternal darkness. The temperature gradient between these hemispheres would be extreme without an atmosphere to redistribute heat. The day side could be scorching while the night side freezes solid, making both regions uninhabitable. But a thick atmosphere changes everything. Atmospheric circulation, driven by that extreme temperature gradient, would create powerful winds that carry heat from the day side to the night side. Climate models show that even a moderately dense atmosphere could prevent the night side from freezing, maintaining temperatures across the planet within a range where liquid water could exist. The most habitable region might not be the day side or the night side but the terminator, the twilight zone between them. Here, the star hangs perpetually at the horizon, neither rising nor setting, providing constant but moderate illumination. The temperature would be milder than the day side, warmer than the night side. If TRAPPIST-1E has water, the terminator region might host a ring of habitable conditions circling the entire planet. This assumes the atmosphere remains stable, which brings us back to the stellar wind problem. TRAPPIST-1 is magnetically active, producing a stellar wind that could strip away atmospheres over hundreds of millions to billions of years. The fact that TRAPPIST-1E might still have an atmosphere after being between 5 and 10 billion years old suggests something is protecting it. That something could be a magnetic field. Earth's magnetic field, generated by a liquid iron core, deflects the solar wind and prevents our atmosphere from being stripped away. Mars lost most of its atmosphere because its magnetic field shut down billions of years ago, leaving the planet defenseless against the solar wind. If TRAPPIST-1E has maintained a magnetic field for billions of years, it could have held on to its atmosphere despite the stellar bombardment. Or the planet might simply have started with so much atmosphere that even billions of years of stripping haven't removed it all. Or volcanic activity could be continuously replenishing gases faster than they're lost to space. Any of these mechanisms could work. The key point is that if TRAPPIST-1E has an atmosphere now, it survived a hostile environment for an incredibly long time. That survival would tell us something profound about planetary resilience. It would demonstrate that Earth-sized rocky planets can maintain habitable conditions around ultra-cool dwarf stars despite intense stellar activity. And since ultra-cool dwarfs make up the vast majority of stars in the galaxy, that would massively expand the number of potentially habitable worlds in the universe. The evidence for or against an atmosphere comes down to a handful of measurements, each one pushing the limits of what our telescopes can detect. James Webb Space Telescope observations between 2022 and 2024 have given us 4 transits of TRAPPIST-1E for moments when the planet passed in front of its star and allowed starlight to filter through any atmosphere that might exist. Those observations hint at something, maybe methane in the atmosphere, but the signal is weak and ambiguous. The problem is the star itself. TRAPPIST-1 is magnetically active in ways that make interpretation difficult. The star produces flares, sudden bursts of energy that temporarily change its brightness and spectrum. It has a strong magnetic field averaging around 600 Gauss, possibly higher, driving intense chromospheric activity. During a transit observation, any signal we detect could be coming from the planet's atmosphere or from the star's own atmospheric variations. Separating the two requires extremely precise measurements and sophisticated modeling. Current data suggests that if TRAPPIST-1E has an atmosphere, it's not a puffy hydrogen envelope like a mini-Neptune. Those have been ruled out. What remains possible is a compact atmosphere similar to Earth's, dominated by nitrogen with traces of other gases, or a completely bare rock with no atmosphere at all. We're essentially at 50-50 odds based on existing observations. The most recent analysis in 2025 couldn't confirm an atmosphere with confidence. Scientists examined the 4 transit observations using multiple analysis methods, comparing the observed spectrum against models of various atmospheric compositions. The results were frustratingly inconclusive. Some analysis methods favored a thin atmosphere. Others favored bare rock. The differences between models fell within the margin of measurement error. What this tells us is that TRAPPIST-1E's atmosphere, if it exists, is subtle enough that we're operating right at the edge of detection capability. We need more data, which is exactly what's coming. A new observing program approved for James Webb involves 15 additional transits of both TRAPPIST-1E and its neighboring planet TRAPPIST-1b. This program uses an innovative strategy. TRAPPIST-1b, the innermost planet, orbits so close to the star that any atmosphere it once had is almost certainly gone, stripped away by stellar radiation and wind. It's likely a bare rock. By observing TRAPPIST-1B and TRAPPIST-1E back-to-back during the same observing sessions, scientists can use TRAPPIST-1B as a reference. Any signal detected during the TRAPPIST-1B transit must be coming from the star, not the planet. That signal can then be subtracted from the TRAPPIST-1E observations, removing stellar contamination and revealing what, if anything, is genuinely coming from TRAPPIST-1E's atmosphere. This technique represents a breakthrough in exoplanet characterization. For years, stellar activity has been one of the biggest obstacles to studying small rocky planets around active stars. Red dwarfs like TRAPPIST-1 are magnetically turbulent, and their variability can mimic or mask atmospheric signals. Using a neighboring bare rock planet as a calibrator bypasses this problem, turning a limitation into a tool. If TRAPPIST-1E has an atmosphere, these observations should finally detect it. If it doesn't, we'll know that too. Either answer changes what we understand about planetary habitability around ultra-cool dwarfs. Beyond James Webb, another mission is targeting TRAPPIST-1E specifically. NASA's Pandora satellite, scheduled to launch in early 2026, is designed to study exoplanet atmospheres and their host stars simultaneously. Pandora won't have the raw sensitivity of James Webb, but it will observe TRAPPIST-1E repeatedly over extended periods, building up a dataset that captures how the star's activity varies over time. By correlating those variations with transit observations, Pandora can help disentangle stellar noise from planetary signals. The satellite represents a new approach, using long-term monitoring rather than individual deep observations to characterize small rocky worlds around variable stars. What would it mean if TRAPPIST-1E has an atmosphere? First, it would confirm that Earth-sized planets can retain atmospheres around ultra-cool dwarf stars despite billions of years of stellar bombardment. That's not guaranteed. TRAPPIST-1 has been magnetically active for its entire lifetime, producing flares and coronal mass ejections that blast the inner planets with radiation and charged particles. The stellar wind pressure at TRAPPIST-1E's orbit may be 1,000 times stronger than the solar wind at Earth's orbit. Under those conditions, atmospheric loss should be rapid. Yet if TRAPPIST-1E still has an atmosphere after 5 to 10 billion years, something has protected it. The most likely protection is a magnetic field. Earth's magnetic field, generated by convection in its liquid iron core, deflects the solar wind and prevents atmospheric stripping. Mars lost most of its atmosphere because its core cooled and its magnetic field shut down, leaving the planet exposed. If TRAPPIST-1E has maintained an active magnetic dynamo for billions of years, it could have shielded its atmosphere from the worst of the stellar assault. That would require a hot interior, kept warm by radioactive decay and possibly tidal heating from gravitational interactions with the other planets in the system. TRAPPIST-1E orbits in resonance with its neighbors, meaning they exert periodic gravitational tugs that flex the planet's interior, generating heat through friction. That heat could drive volcanism, which would replenish atmospheric gases even as they're stripped away by the stellar wind. The alternative is that TRAPPIST-1E started with so much atmosphere that it hasn't lost it all yet. Imagine a planet that formed with a thick volatile-rich envelope, hundreds or thousands of times the atmospheric mass of Earth. Even billions of years of stripping might leave a substantial atmosphere remaining. This scenario is plausible for planets that formed farther out in the system and migrated inward, carrying volatiles with them from colder regions. Evidence suggests all 7 TRAPPIST-1 planets migrated together as a resonant chain, moving inward from their formation locations. During that migration, they could have accumulated significant amounts of water and other volatiles. If TRAPPIST-1E has retained an atmosphere, the composition matters as much as the presence. An atmosphere dominated by carbon dioxide would create a greenhouse effect, warming the surface above the equilibrium temperature and potentially maintaining liquid water even with lower stellar flux. Models show that as little as 0.2 bars of CO2, about a fifth of Earth's atmospheric pressure, could be enough to keep TRAPPIST-1E's surface above freezing. With more CO2, 5 bars or 10 bars, the planet could be significantly warmer, possibly too warm for life as we know it but still within the range of habitability for extremophiles. An atmosphere with nitrogen and oxygen would be even more interesting. Oxygen in particular is a biosignature, a gas that doesn't persist in planetary atmospheres without continuous replenishment by life. On Earth, oxygen makes up 21% of the atmosphere because photosynthetic organisms continuously produce it. Without life, Earth's oxygen would disappear within a few million years, consumed by chemical reactions with rocks and gases. If we detected significant oxygen in TRAPPIST-1E's atmosphere, it would be one of the strongest hints of life we could find without actually going there. That's why the search for atmospheric oxygen on rocky exoplanets is such a high priority. It's not definitive proof of life, but it's close. Methane is another biosignature, though less definitive than oxygen. Methane can be produced by geological processes, especially volcanism, but it can also be produced by microbial life. On Earth, most methane in the atmosphere comes from biological sources, primarily methanogenic bacteria. If TRAPPIST-1E has both methane and oxygen in its atmosphere simultaneously, that would be a powerful biosignature combination. Methane and oxygen react with each other and don't coexist in equilibrium. Finding both together would suggest active replenishment by life. The tentative hints of methane in early James Webb observations are intriguing for this reason, though as noted, those hints might be stellar contamination rather than genuine planetary signals. Climate models for TRAPPIST-1E explore a wide range of atmospheric compositions and surface conditions. The TRAPPIST-1 Habitable Atmosphere Intercomparison Project, known as TRAPPIST, brings together multiple climate modeling groups to simulate different scenarios. These models test what happens with varying amounts of CO2, different surface types, ocean coverage, cloud behavior, and atmospheric circulation patterns. Results consistently show that TRAPPIST-1E could maintain surface temperatures above freezing with relatively modest greenhouse warming. The planet's equilibrium temperature without an atmosphere ranges from 225 to 246 Kelvin depending on albedo, well below freezing. But with even a thin atmosphere containing greenhouse gases, surface temperatures rise into the habitable range. The terminator region, the boundary between the day and night sides, emerges as particularly interesting in these models. On a tidally locked planet, the terminator experiences perpetual twilight. The star hangs at the horizon, neither rising nor setting. Temperature gradients are moderate compared to the extreme heat of the day side and extreme cold of the night side. If TRAPPIST-1E has surface water, the terminator might host a habitable ring circling the entire planet, a zone where temperatures and light levels remain stable enough for liquid water and potentially life. These models assume the atmosphere circulates efficiently enough to redistribute heat. That's not guaranteed on a tidally locked world. Atmospheric circulation depends on the temperature difference between the day and night sides, the planet's rotation rate, and the atmosphere's thickness and composition. Weak atmospheric circulation could create a situation where the day side overheats while the night side freezes, leaving no stable temperate zone. Strong circulation, driven by powerful winds and weather systems, could smooth out temperature extremes and create habitable conditions across much of the planet's surface. The specific outcome depends on variables we can't yet measure from 40 light-years away. Tidal locking creates another unusual feature worth considering. On Earth, day and night alternate as the planet rotates. Life evolved with circadian rhythms tied to this cycle. Plants photosynthesize during the day and respire at night. Animals have sleep-wake cycles synchronized to the day-night pattern. On TRAPPIST-1E, there is no day-night cycle. The day side experiences permanent day. The night side experiences permanent night. The terminator experiences perpetual twilight. How would life adapt to such conditions? On the day side, organisms would need protection from constant exposure to starlight and heat. Deep shade might not exist anywhere. Water evaporation would be relentless. On the night side, organisms would need to function in permanent darkness and cold. Energy sources would be limited to chemical processes or geothermal heat rather than photosynthesis. At the terminator, the environment might be most Earth-like, with moderate temperatures and dim but constant light levels. If photosynthesis occurred, it would be optimized for low light levels and the infrared heavy spectrum of TRAPPIST-1's radiation. Plants might appear black rather than green, absorbing as much of the available light as possible across all wavelengths. These speculations assume TRAPPIST-1E has liquid water and an atmosphere capable of supporting life. That remains uncertain. The gravity on TRAPPIST-1E deserves attention. At 82% of Earth's gravity, the difference would be noticeable but not extreme. You'd feel lighter, able to jump higher and carry heavier loads with less effort. Water would flow slightly differently. Rain would fall more slowly. The lower gravity affects how atmospheres behave and how geological processes operate. A thinner crust might be more prone to volcanic activity. Volcanic outgassing could be crucial for maintaining an atmosphere over billions of years, especially if stellar winds constantly strip atmospheric gases away. Active volcanism releases carbon dioxide, water vapor, sulfur compounds, and other gases that replenish atmospheric losses. Earth's atmosphere would have been stripped away long ago without volcanic replenishment. TRAPPIST-1E might depend on the same process. Plate tectonics could also play a role. On Earth, plate tectonics recycles carbon between the atmosphere and the interior, regulating climate over geological timescales. This carbon cycle acts as a planetary thermostat. Too much CO2 causes warming, which accelerates weathering of rocks, which pulls CO2 out of the atmosphere and locks it into minerals. Too little CO2 causes cooling, which slows weathering, allowing volcanic outgassing to build CO2 back up. Whether TRAPPIST-1E has plate tectonics is unknown. The planet's size and internal heat suggest it might. The gravitational interactions with neighboring planets could generate tidal heating, keeping the interior molten and geologically active. These tidal forces arise because TRAPPIST-1E orbits in a resonant chain with the other planets. Their gravitational tugs flex the planet's interior, generating heat through friction. The same process keeps Jupiter's moon Io volcanically active despite its small size and great distance from the Sun. For TRAPPIST-1E, tidal heating could be an additional energy source beyond stellar radiation, potentially warming the planet from within and driving geological activity that supports habitability. The resonant orbital configuration of the TRAPPIST-1 system is remarkable. The 7 planets orbit in near-perfect integer ratios. If you measured the time it takes each planet to complete one orbit and compared them, you'd find patterns like 3 to 2 or 5 to 3. This isn't coincidence. It's a sign the planets migrated inward together from farther out in the protoplanetary disk, locking into gravitational resonances as they moved. These resonances stabilize the system, preventing collisions despite the planet's close proximity. The orbital periods range from 1.5 days for the innermost planet to just 19 days for the outermost. All 7 planets orbit closer to their star than Mercury orbits the Sun. The entire system would fit comfortably inside Mercury's orbit with room to spare. From TRAPPIST 1E's surface, the other planets would be visible to the naked eye, not as points of light but as distinct disks. Some would appear larger than the Moon appears from Earth. You could watch them move across the sky in real time, their positions shifting noticeably over the course of hours. The sky would be crowded with worlds, each one a nearby neighbor in a tightly packed planetary family. This proximity creates another factor affecting habitability. The planets exchange material. Asteroid impacts on one planet could eject rocks into space that eventually land on another planet, carrying microbes if they exist. This process, called panspermia, could spread life throughout the system if it emerged on any one planet. The close spacing makes interplanetary travel of biological material much more likely than in our solar system. Life on TRAPPIST-1E might have originated on TRAPPIST-1D or TRAPPIST-1F and migrated via meteorite impact. Or life on TRAPPIST-1E could seed the other habitable zone planets. The system could host multiple biospheres descended from a common origin. Studying TRAPPIST-1 forces us to reconsider what habitable means. Earth-like conditions are one possibility, but not the only one. TRAPPIST-1E receives less light than Earth, experiences tidal locking, orbits an active flare star, and might have a completely different atmospheric composition and water inventory than our planet. Yet it could still be habitable. Life might thrive in conditions we'd consider marginal or even hostile. The Terminator Zone offers one habitat. Subsurface oceans insulated from surface extremes offer another. Volcanic vents provide energy for chemosynthetic ecosystems independent of starlight. Life is adaptable. The question isn't whether TRAPPIST-1E is identical to Earth, but whether it provides the basic ingredients, liquid water, energy sources, and stable conditions over long timescales. Current evidence suggests it might. The age of the system is important here. TRAPPIST-1 is between 5.5 and 9.5 billion years old, potentially twice the age of our solar system. If TRAPPIST-1E has been habitable for even a fraction of that time, life there has had far longer to evolve than life on Earth. Earth's biosphere is 4 billion years old. Multicellular life emerged less than 1 billion years ago. Complex animals appeared only in the last 600 million years. If TRAPPIST-1E has had stable habitable conditions for 8 billion years, what might have evolved there? Single-celled organisms certainly. But beyond that, we can only speculate. Intelligence might have emerged and gone extinct multiple times over such vast timescales. Or life might remain microbial, filling ecological niches but never developing complexity. The longer timescale doesn't guarantee complexity, but it allows more opportunities for evolutionary experiments. Earth's history shows mass extinctions reset the trajectory of life repeatedly. A similar pattern might occur on TRAPPIST-1E, with stellar flares causing periodic atmospheric stripping events that stress or eliminate surface life while subsurface ecosystems survive. The star itself provides both opportunity and challenge. TRAPPIST-1 will shine for 10 trillion years, 700 times longer than the current age of the universe. It's barely begun its lifespan. The Sun, by contrast, will exhaust its hydrogen fuel and leave the main sequence in about 5 billion years, rendering Earth uninhabitable long before it dies. TRAPPIST-1E has time. More time than any planet in our solar system will ever have. That longevity means the search for life on TRAPPIST-1E isn't just about finding life as it exists now, but understanding whether life can emerge, persist, and evolve over timescales that dwarf anything we've experienced. The implications extend beyond biology. Understanding how life emerges and evolves in one environment versus another tells us something fundamental about the universe itself. Is Earth's path typical or exceptional? The answer matters. If TRAPPIST-1E developed life independently, convergent evolution becomes testable. Do separate biospheres produce similar solutions to similar problems? Does DNA emerge inevitably, or was that molecular choice arbitrary? If we found life on TRAPPIST-1E that used different information storage molecules, different energy pathways, different cellular architectures, it would prove life's flexibility exceeds our current models. But there's a darker possibility. TRAPPIST-1E might be sterile. Not because it lacks water or energy, but because stellar flares sterilize the surface repeatedly. Each major flare strips away atmospheric layers, bombards the surface with radiation, resets any progress toward complexity. Life might emerge during quiet periods only to be extinguished during active phases. The cycle could repeat endlessly. Single-celled organisms might evolve, thrive briefly, then vanish when the next flare hits. The planet becomes a biological treadmill where complexity never gains traction. This scenario isn't speculation. We know TRAPPIST-1 produces 42 flares every 80 days based on Kepler observations. Large, complex flares capable of altering planetary atmospheres significantly. The star's magnetic field averages 600 Gauss, though that might be underestimated. Magnetic activity drives chromospheric chaos. Coronal mass ejections might be trapped by the field, concentrating their energy near the planets. The stellar wind pressure could be 1,000 times stronger than what Earth experiences from the Sun. That wind could strip atmospheres from planets up to TRAPPIST-1F over timescales ranging from 100 million to 10 billion years. Yet TRAPPIST-1E has survived for billions of years already. If it has an atmosphere now, something is replenishing what the star strips away. Volcanic outgassing is the obvious candidate. Tidal heating from gravitational interactions with neighboring planets could drive intense geological activity. The planet might possess a partially molten interior that continually releases gases to the surface. Volcanic vents would pump water vapor, carbon dioxide, sulfur compounds into the atmosphere faster than stellar wind removes them. The balance between loss and replenishment determines whether a stable atmosphere persists. This creates a tension. Volcanic activity provides atmospheric replenishment but also surface hazards. Frequent eruptions reshape landscapes, bury ecosystems under lava flows, inject ash into the atmosphere that blocks light and cools the climate temporarily. Life would need to adapt to geological instability as well as stellar instability. Organisms might evolve rapid dispersal mechanisms, spreading across the planet quickly after each catastrophe. Or they might retreat underground during surface upheavals, emerging when conditions stabilize. Subsurface life becomes more attractive in this context. The planet's density offers clues about internal structure. At 5.65 grams per cubic centimeter, TRAPPIST-1E is slightly denser than Earth. That implies a similar composition: iron core, silicate mantle, rocky crust. But the exact ratios might differ. TRAPPIST-1 planets are about 8% less dense than expected if they matched Earth's composition precisely. They might contain more water locked-in minerals, or different iron-to-silicate ratios. These differences affect heat transport, magnetic field generation, tectonic activity. A planet without plate tectonics might lack the recycling mechanisms that stabilize Earth's climate over geological time. Or it might develop alternative stabilization through different feedback loops. Water inventory matters enormously. Climate models show TRAPPIST-1E could retain water equivalent to several Earth oceans. That water might exist as ice beneath the surface, liquid oceans covering the planet, or atmospheric vapor cycling between day and night sides. A water world with global oceans hundreds of kilometers deep creates radically different conditions than Earth. No exposed land means no weathering cycles that regulate atmospheric carbon dioxide. Ocean chemistry becomes the dominant climate regulator. Deep oceans might develop layered structures with different temperatures, pressures, chemistries at various depths. Life could occupy multiple ecological zones vertically as well as horizontally. But here's what makes TRAPPIST-1E particularly fascinating from a habitability perspective: the terminator zone. This narrow band between permanent day and permanent night might host the most stable conditions on the planet. Not too hot, not too cold. Stellar radiation arrives at an angle rather than directly overhead, reducing intensity without eliminating it entirely. Atmospheric circulation would concentrate here, redistributing heat from the day side and moisture from the night side. If liquid water exists anywhere on the surface, the terminator is the most likely location. Standing in the terminator zone, you'd see the star perpetually near the horizon, never rising or setting. The sky would glow orange-red where the star sits, fading to deep twilight overhead, and complete darkness toward the night side. Weather patterns would be unlike anything on Earth. Winds would howl constantly as hot air from the day side rushes toward the cold night side. Clouds might form and dissipate in minutes as moisture cycles through the narrow habitable band. Rain could fall continuously in some regions, while others remain perpetually dry. The ground might be warm from internal heat but never scorching from direct starlight. This environment selects for specific adaptations. Plants, if they exist, would grow horizontally toward the light source rather than vertically. They'd need to tolerate low light levels and produce pigments tuned to infrared rather than visible wavelengths. Animals would navigate by the star's position, using it as a permanent compass. Circadian rhythms wouldn't exist in the traditional sense. Life cycles might key to stellar flares instead, with organisms timing reproduction or dormancy to avoid peak radiation events. The possibility of photosynthesis on TRAPPIST-1E remains uncertain. Infrared light carries less energy per photon than visible light. Organisms would need to capture more photons to generate the same energy output. This might favor larger light-gathering structures or different photosynthetic pathways altogether. Earth's photosynthesis uses chlorophyll, which absorbs red and blue light while reflecting green. TRAPPIST-1E's photosynthesizers might absorb infrared and near-red, appearing nearly black to human eyes. Forests would look dark and alien, absorbing almost all incoming light. But photosynthesis isn't the only energy pathway. Chemosynthesis, the process used by organisms near Earth's deep-sea vents, works independently of light. These organisms extract energy from chemical reactions involving hydrogen sulfide, methane, or iron compounds. TRAPPIST-1E's volcanic activity could support extensive chemosynthetic ecosystems. Life might thrive in darkness, feeding on volcanic emissions. Surface organisms could use photosynthesis during quiet periods while subsurface organisms maintain continuity through chemosynthesis regardless of surface conditions. The question of atmospheric composition remains unresolved. James Webb observations have given us 4 transits worth of data. Not enough to definitively confirm or rule out an atmosphere. The most recent analysis in 2025 couldn't conclude with confidence either way, though it ruled out certain scenarios. A cloud-free hydrogen-dominated atmosphere doesn't exist. If TRAPPIST-1E has air, it's more compact, more like terrestrial planets than gas giants. 2 scenarios remain viable. First, a nitrogen-dominated atmosphere similar to Earth's, possibly with traces of methane. Second, a bare rocky surface with no substantial atmosphere. The data currently supports both equally. We need more observations. NASA's Pandora mission, scheduled to launch in early 2026, should help. This small satellite is designed specifically to characterize exoplanet atmospheres and their host stars. Pandora will observe multiple transits of TRAPPIST-1 planets, building a more complete dataset. There's also a new JWST observing program underway. 15 additional observations targeting TRAPPIST-1E and its neighbor TRAPPIST-1B. The strategy is clever. TRAPPIST-1B is believed to be a bare rock with no atmosphere. By observing back-to-back transits of both planets, scientists can use TRAPPIST-1B's signal as a reference. The star's activity affects both planets identically. Any difference between their signals must come from TRAPPIST-1E's atmosphere if it exists. This technique, using one planet to correct for stellar contamination of another, represents a breakthrough in exoplanet characterization. The challenge stems from stellar activity itself. Red dwarfs like TRAPPIST-1 are magnetically active. Their surface is royal with star spots, flares, and convection cells. These features create noise in the data that mimics atmospheric signals. Separating planet from star requires precision measurements repeated many times. Each transit provides one data point. 4 transits aren't enough to average out stellar noise. 15 might be. 30 would be better. What we learn from TRAPPIST-1E will inform searches for life on other planets. If we detect an atmosphere, we'll know that planets around red dwarfs can retain air despite stellar activity. That expands the habitable zone of the galaxy significantly. Red dwarfs outnumber Sun-like stars 10 to 1. If their planets can host life, the number of potentially habitable worlds increases dramatically. If TRAPPIST-1E lacks an atmosphere, we'll know that stellar activity strips air from close-orbiting planets, limiting habitability to more distant orbits or different stellar types. Either answer matters. Negative results constrain possibilities as much as positive results expand them. Science progresses through elimination as well as discovery. The bigger question isn't just about TRAPPIST-1E. It's about what this planet represents in the search for life beyond Earth. We've spent decades looking at stars like our Sun, yellow dwarfs with stable outputs and well-behaved temperaments. But those stars make up only a fraction of the galaxy. Red dwarfs outnumber them 10 to 1. If planets around red dwarfs can host life, the number of potentially habitable worlds explodes. TRAPPIST-1E forces us to confront assumptions we didn't know we were making. We assumed habitable planets need Earth-like orbits, Earth-like day lengths, Earth-like stellar radiation. TRAPPIST-1E challenges every one of those assumptions. It orbits once every 6 days. It's tidally locked. It receives predominantly infrared radiation. Yet it might still harbor life. The implications extend beyond biology. They touch on planetary formation, atmospheric evolution, the limits of habitability. If TRAPPIST-1E has retained an atmosphere after billions of years of stellar bombardment, that tells us something profound about atmospheric retention mechanisms. Volcanic outgassing might replenish losses. Magnetic fields might shield against stellar wind. Gravitational interactions with sibling planets might generate internal heat that drives geological activity. The system's age matters here. TRAPPIST-1 is between 5 and 10 billion years old, potentially twice Earth's age. Life on Earth appeared relatively quickly once conditions stabilized, within a few 100 million years. If similar processes occurred on TRAPPIST-1E, life there could have billions of years head start. Not millions. Billions. That's enough time for remarkable complexity to develop. Earth went from single cells to multicellular organisms in about 2 billion years. From multicellular life to intelligence took another 1.5 billion. If TRAPPIST-1E followed similar timelines but started earlier, we might be looking at a world with life far more developed than anything on Earth. Or we might be looking at a barren rock. That's the frustrating beauty of science at this scale. We don't know yet. Can't know until we gather more data. The universe doesn't reveal its secrets on our schedule. The orbital dynamics of the TRAPPIST-1 system add another layer of intrigue. All 7 planets are locked in resonant chains, their orbital periods related by simple integer ratios. This configuration isn't random. It's evidence of orbital migration, planets moving inward from their formation positions, shepherding each other into stable resonances. This process takes time, requires specific conditions. The fact that all 7 planets maintain this configuration suggests the system has been dynamically stable for billions of years. That stability matters for habitability. Planets need time. Time for atmospheres to develop, for water to accumulate, for chemistry to explore the space of possible reactions. Chaotic systems don't provide that time. Planets get ejected, orbits destabilize, collisions occur. TRAPPIST-1's resonant chain indicates none of that has happened. These worlds have maintained their positions, their relationships, their environmental conditions for geological timescales. The resonances also generate tidal heating. As planets pull on each other gravitationally, their orbits shift slightly. These shifts flex the planet's interiors, generating heat through friction. Jupiter's moon Io experiences extreme tidal heating, enough to make it the most volcanically active body in the solar system. TRAPPIST-1E experiences similar forces, though to what degree remains uncertain. Tidal heating could provide an additional energy source beyond stellar radiation, potentially supporting life even if surface conditions seem marginal. Standing on TRAPPIST-1E would be unlike standing anywhere in our solar system. The sky would be dominated by an orange-red star 4 times wider than our Sun appears from Earth. That star wouldn't move. It would hang fixed above the horizon, unchanging. No sunrises, no sunsets. Just perpetual twilight on one hemisphere and eternal darkness on the other. But you wouldn't be alone in the sky. 6 other worlds would be visible, some appearing larger than our moon. They wouldn't be distant points of light like planets appear from Earth. They'd be disks, showing features, moving in complex patterns as they orbit. You could watch TRAPPIST-1F drift across the sky over the course of days. TRAPPIST-1G would move more slowly, taking weeks to cross from horizon to horizon. The inner planets would zip past, completing their journeys in hours. This celestial ballet would be more than scenic. It would have practical implications for any life that developed there. Tidal forces from neighboring planets would create stress patterns in the crust. Earthquakes might synchronize with planetary conjunctions when multiple worlds align. Ocean tides, if oceans exist, would respond not just to the star but to gravitational pulls from multiple sources. Life would need to adapt to these rhythms or exploit them. The question of TRAPPIST-1E's composition remains partially open. Density measurements suggest an Earth-like mix of iron, rock, and possibly water. But the planet is about 8% less dense than it would be with Earth's exact composition. That difference could mean more water, less iron, different mineral ratios. Small differences in composition lead to large differences in geology, atmospheric chemistry, habitability. Water content matters enormously. Too little and you have a dry Mars-like world with limited capacity to support life. Too much and you get a water world with oceans hundreds of kilometers deep, no exposed land, potentially different chemistry at crushing depths. Earth sits in a sweet spot with about 0.02% of its mass as surface water. TRAPPIST-1E might contain several Earth oceans worth of water. Whether that water resides on the surface, in the mantle, or was lost to space billions of years ago remains unknown. The TRAPPIST-1 system gives us 7 laboratories to study planetary evolution under similar conditions. Each planet formed from the same protoplanetary disk, experienced similar early bombardment, aged under the same stellar environment. Yet they differ in distance from the star, in their interactions with each other, potentially in their atmospheres and surface conditions. Comparing them reveals which factors matter most for habitability. TRAPPIST-1b, the innermost planet, is almost certainly too hot. TRAPPIST-1c and d receive too much radiation for comfort. TRAPPIST-1h, the outermost, probably too cold. That leaves E, F, and G in the habitable zone, with E appearing most favorable. But appearances can deceive. We need data, not assumptions. The atmospheric question will likely be resolved within the next few years. 15 more JWST observations are planned. Pandora launches in 2026. Other missions are in development. Each observation adds information, constrains the possibilities, narrows the uncertainty. Eventually we'll know whether TRAPPIST-1E has air or not. And if it does, we'll start characterizing what that air contains. Detection of oxygen would be provocative. On Earth, free oxygen exists because of photosynthesis. Without life constantly producing it, atmospheric oxygen reacts with rocks and disappears. Finding oxygen on TRAPPIST-1E would suggest either life or exotic geological processes we haven't encountered. Either answer would be significant. Methane would be similarly interesting. Methane breaks down quickly under stellar UV radiation. Its presence implies ongoing production, either biological or geological. Combined with other gases, methane signatures could point toward active ecosystems or active geology. Context matters. A planet with methane and oxygen together would be different from a planet with methane alone. But absence of biosignatures wouldn't mean absence of life. Early Earth had life for billions of years before oxygen accumulated. Microbial ecosystems can thrive without producing atmospheric signatures we can detect from 40 light-years away. Non-detection doesn't equal non-existence. It just means we need closer looks, better instruments, more creative thinking about what signatures to search for. The search for life extends beyond atmospheric chemistry. Future telescopes might detect surface features that suggest biology. Seasonal changes in surface coloration could indicate vegetation growth cycles. Anomalous surface chemistry might point toward biological processing of materials. Even simple things like unusual distributions of trace elements could hint at biological concentration mechanisms. TRAPPIST-1E represents a test case for the broader question of life in the universe. If we find life there, we'll know life isn't rare, isn't confined to Earth-like planets orbiting Sun-like stars. If we don't find life despite favorable conditions, we'll learn something equally important about what factors matter most for life's emergence. The planet exists 40 light-years away. Not 40 million. 40. That's close enough to study in detail with current technology. Close enough to imagine sending probes to, someday, with technologies that don't exist yet. Close enough to feel real rather than abstract. We're living through the first era in human history when we can study individual planets around other stars, characterize their atmospheres, assess their habitability. Our grandparents didn't know planets existed beyond our solar system. We know of thousands and can study the most interesting in detail. The pace of discovery is extraordinary. TRAPPIST-1E might have life. It might not. We don't know yet, can't know until we gather more evidence. But the fact that we can ask the question, that we have tools capable of answering it, that we've found a world where the answer matters, that alone is remarkable. That's where we are now. 40 light years from a planet that might rewrite our understanding of life's place in the cosmos. Just waiting for more data to arrive. So what happens next? The answer is both frustratingly simple and maddeningly complex. We wait. But that waiting isn't passive. It's active observation, careful analysis, building datasets that will eventually answer whether TRAPPIST-1E has an atmosphere or not. The 15 additional JWST observations represent humanity's best current effort to pierce through 40 light-years of space and determine if air exists around this world. Using TRAPPIST-1B as a reference planet is clever enough that it might actually work. Subtract stellar noise from both signals, see what remains. If something remains in TRAPPIST-1E's data but not TRAPPIST-1B's, that's atmosphere. If both planets show identical signals, that's bare rock. Pandora launching in 2026 adds another tool. Long-term monitoring fills gaps that individual deep observations can't address. Stellar variability averaged over months or years reveals patterns that single transits miss. Combined datasets from multiple instruments, multiple observing strategies, multiple analysis methods will eventually converge on an answer. Maybe not the answer we want, but an answer grounded in evidence rather than hope. The broader implications extend far beyond one planet. If TRAPPIST-1E has retained an atmosphere after billions of years orbiting an active red dwarf, that fundamentally changes habitability calculations for the galaxy. Red dwarfs outnumber Sun-like stars dramatically. They comprise roughly 70% of all stars in the Milky Way. Most of those red dwarfs host planets. If those planets can maintain atmospheres and support life despite stellar activity, the number of potentially habitable worlds increases by orders of magnitude. We're not just studying TRAPPIST-1E. We're studying whether the most common type of planetary system in the galaxy can host life. That's why this matters. That's why 15 telescope observations of one planet justify the time and resources. The answer scales up to billions of worlds. And if TRAPPIST-1E lacks an atmosphere, that answer matters too. It tells us stellar activity wins, that close-orbiting planets around red dwarfs can't hold on to air long enough for life to develop. It narrows the habitable zone of the galaxy, focuses future searches on different stellar types or more distant orbits. Negative results constrain the search space as effectively as positive results expand it. The age of the system keeps pulling me back. Between 5 and 10 billion years old. Twice Earth's age potentially. Life on Earth appeared within a few hundred million years once conditions stabilized. Intelligence took billions of years after that. If TRAPPIST-1E has been habitable for 8 billion years, and if life emerged there at similar pace to Earth, we might be looking at a biosphere with billions of years developmental head start on ours. Not millions of years. Billions. That thought experiment requires massive assumptions. It assumes life emerges readily given the right conditions. It assumes evolutionary paths toward complexity are inevitable rather than contingent. It assumes TRAPPIST, TRAPPIST-1E has remained habitable continuously rather than experiencing sterilizing events. Each assumption might be wrong. Probably some are wrong. But the possibility remains. We don't know enough yet to rule it out. The view from that world's surface would be extraordinary. 6 sibling planets visible in the sky, some appearing larger than our moon. The star hanging fixed at the horizon, glowing orange-red, never moving. The terminator zone where you'd stand, experiencing perpetual twilight, watching worlds drift overhead in complex orbital patterns. Weather systems howling as hot dayside air rushes toward the frozen night side. Volcanic vents perhaps, releasing gases that feed chemosynthetic ecosystems in the darkness. These aren't fantasies. They're possibilities grounded in physics and observation. We know the planet exists. We know its size, mass, density, orbit. We know the star's properties, the system's architecture, the gravitational interactions between planets. What we don't know is whether those conditions add up to habitability. That's what the observations are for. The frustrating part is timescale. Science doesn't work on demand. Observations take time to schedule, execute, analyze. JWST is oversubscribed by factors of 5 to 10. Every observation of TRAPPIST-1E means something else doesn't get observed. Priorities compete. Time allocates slowly. The 15 additional observations will happen over months or years, not weeks. Pandora won't launch until 2026, won't produce results immediately after launch. We're talking years before definitive answers arrive. But definitive answers will arrive. That's the difference between now and 20 years ago. 20 years ago, we could barely detect planets around other stars, let alone characterize them. Now we're measuring atmospheric composition of Earth-sized worlds 40 light-years away. The technology exists. The questions are answerable. We just need patience and data. TRAPPIST-1E forces us to expand our definition of habitable. Earth-like conditions are one path to life, but maybe not the only path. Tidal locking doesn't automatically disqualify a world. Heavy stellar activity doesn't automatically sterilize it. Lower stellar flux doesn't automatically freeze it. The universe is larger and stranger than our Earth-centered intuitions suggest. Life might thrive in conditions we consider marginal or hostile. That possibility matters philosophically as much as scientifically. Are we alone? The question has haunted humans for millennia. TRAPPIST-1E won't definitively answer that question, not by itself. But it will narrow the uncertainty. If we find an atmosphere, especially one with biosignatures, the probability of life existing elsewhere increases dramatically. If we find bare rock on a planet that should be habitable, that constrains where and how life can emerge. Either answer moves us forward. Either answer provides information we don't currently have. That's the value of the search itself, not just potential discoveries. Every observation, every measurement, every analysis adds to collective knowledge about how planets work, how atmospheres evolve, how life might emerge or fail to emerge given specific conditions. The TRAPPIST-1 system gives us 7 test cases. 7 planets that formed together, evolved under similar conditions, but differ in their distances from the star and their interactions with each other. Comparative planetology at its finest. We can study how location in the habitable zone affects outcomes, how planetary mass influences atmospheric retention, how tidal forces impact geology. Each planet teaches something about planetary science generally, not just about individual worlds. And TRAPPIST-1E sits right in the middle of that habitable zone. Not too close, not too far. Similar size to Earth. Similar density. Similar gravity. If any planet in the system has held on to an atmosphere and maintained habitable conditions, TRAPPIST-1E is the best bet. That's why it's the focus. That's why 15 JWST observations target it specifically. The stakes feel high because they are high. This isn't just academic curiosity. It's foundational questions about life's place in the universe. Are Earth and humanity unique? Or are we common, replicated across billions of worlds throughout the galaxy? TRAPPIST-1E can't answer that completely, but it can provide crucial evidence one direction or another. We're standing at a threshold. Previous generations wondered if planets existed around other stars. We know they do. Previous generations wondered if Earth-sized planets existed in habitable zones. We know they do. Now we're asking whether those planets actually host life. That's the next question, the one our generation gets to investigate. TRAPPIST-1E represents that investigation's leading edge. A planet we can study in detail, close enough for meaningful observations, interesting enough to justify the effort. The observations are happening now. The data is accumulating. Within a few years, we'll know whether it has an atmosphere. Within a decade, we might know what that atmosphere contains. Within a generation, we might have direct evidence of life or its absence. That timeline feels slow from a human perspective. But it's extraordinarily fast from a historical one. The universe is old. The question of life beyond Earth is ancient. We're answering it in real time, using instruments that didn't exist a few years ago, analyzing data our grandparents couldn't have imagined collecting. The planet is there, 40 light-years away, orbiting its small red star with 6 siblings, possibly harboring oceans, possibly hosting life, possibly covered in dark forests optimized for infrared light, or possibly barren, sterile, a reminder that habitability alone doesn't guarantee biology. We don't know yet. We will soon. That's where the story stands. Not at an ending, but at a pivot point. TRAPPIST-1E exists. We've found it, measured it, begun characterizing it. The next chapters will determine what it means. Whether it changes everything we thought we knew about life in the universe, or whether it confirms our loneliness, or whether it adds one more data point to a question that will take centuries to fully answer. What matters is that we're asking. What matters is that we have tools capable of providing answers. What matters is that a planet 40 light-years away, orbiting a star that will shine for trillions of years, has become more than a point of light in the sky. It's become a destination, a question, a possibility that might reshape how we understand our place among the stars.